play around with them. The last talk, and let me get this in my hand. In this session is a work in progress talk. It's a scheduled partial credit RL for reliable code generation with small language models. And Suryansh Singh Sijwali is going to present it. You're from Penn State, is that? So, thank you. So, the mic is here. Thank you. Thank you. Okay, so it's 10 minutes. What I'll do is I'll give you a finger saying 2 minutes or so to go. All right? Yeah.
Do you have an HDMI connector?
Do you need
I think so, yeah. Let me try. Oh, no, it works. Yeah, I thought I was missing a part. Oh. Hello everyone. So to present this, all right. So I'll be presenting this checkpoint of our overall work that focuses on improving code generation processes in small language model. So here we are focusing specifically on scheduled partial credit RL pipeline, and I have configured the presentation into answering 4 specific questions, which are why, what, how, and what's next. So answering why first. So why are we focusing on small language models specifically? We all know that LLMs are like pretty good at code generation. They're beating benchmarks every second month. So why are we specifically focusing on small language models? So the very direct answer would be that small language models can really fit inside of our specific deployment, inside of PCs, inside of edge devices. And if you go very small, you can also fit them inside of some embedded systems. And what is the problem that we are really solving? Because there are small language models that are fine-tuned for code generation. Now, the thing we found out was that these fine-tuned models usually produce only 50% of syntax valid code, which is a really big issue because these models promise really good security or secure code, but only 50% of them are actually syntax valid. So there is a big loophole in there. What does our work specifically entail? We also set out to solve the security paradigm, but the issue is not really security. The issue is compilation, because a lot of these models actually promise more than 80% of security valid code, security clean code. But if you go in deeper and analyze the secure code, you find out that 50% of them are stubs that don't really even compile. But since they don't have a vulnerability that can be caught by an SAST tool, it comes out as secure clean, but the code actually does not even compile. So we found out that reliability is something that we have to focus on. We have to focus on code that actually compiles first, and then we can focus on security. So we pivoted to producing code that actually compiles and is syntax valid first. And for that, we created a joint reward, which basically prioritizes code functionality over code security. So how does this solve the problem? We started off by selecting a baseline, which is very low in terms of the number of parameters, which is 1.3 billion. This is a pre-fine-tuned version, so DeepSeek Coder is fine-tuned for coding. But even so, the baseline only produces about 20% syntax valid code. So we applied a LoRa-based supervised fine-tuning pipeline, and we use apps plus dataset as the baseline for the fine-tuning. This only fine-tuned about 0.43% of the total number of parameters. So total number is 1.3 billion. We fine-tuned close to like 60 million. And this was only behavioral fine-tuning, and we did not really do anything with how the model produces code. And we saw significant improvement there, but the main RL portion comes next. So after we got the supervised fine-tuned model, we ran it through a PPO training pipeline, which consisted of a double reward setup, which included a functionality reward and a security reward. The security reward consisted of the banded SSD2. The functionality reward basically consisted of how many test cases it's passing. And from that, we got our main model that we'll be evaluating later. And how did this solve the problem? So the main problem we face when evaluating or when training small language models is that the reward is too sparse. So the model finds it really difficult to learn anything based on the binary rewards. So we broke down the reward into partial credits, so it can sort of have a ladder to climb. We set up like specific milestones for the functionality reward, so it can be easier to train it. If it's syntax valid, that's like the minimal requirement, it will get at least some reward. And then if it's passing more and more test cases, it's getting the full reward. And to maintain the security part of our reward, we had a guardrail using medium and hard security vulnerabilities. If there are any, it will basically not give any positive reward to the model, and the reward will degrade. So the model is forced to maintain security while also focusing on reliability. And the result we got was pretty significant. So as I did mention, that binary reward is really sparse when we go down the scale in terms of small language model training. So the binary reward actually is worse than what we got for our SFT model. We only got 18% syntax valid, which is like 26 percentage points less than even the baseline. This happens because just using a 0 or 1 for functionality does not really teach the model anything at this scale. Because just think about it this way, if you don't know about a specific topic and you're attempting it, you won't be able to learn without any feedback what you're doing wrong, right? So it's difficult for the model to explore and gain any insight about what's wrong and what's right. With the partial credit, it improves slightly, but what really helps is a schedule framework. So we give our model a warm start using the binary framework and then move on to partial credit. So it has a very rigorous exploration set up by the binary because it's not able to learn anything, so it has to explore by its own. And with the partial credit, it's sort of smoothened. And because of that, we get a really high syntax validity score in our curriculum model. Now, this is just what we have done so far. Since this is work in progress, there's a lot we can do in the future as well. The very first thing would be to tighten the reliability result. That's because our current version does not really have a very tightly bounded CI. So we can probably run more seeds, run more steps to get it to like plus minus 2%, I guess. And secondly, we can also fix the hyperparameters and ensure that we are using the best ones. We can run a rank-based ablation for our fine-tuning platform. We can also play around with the learning rates. There's a lot of other ablations we can do. We can generalize the small language models and try it on different RL algorithms. For this, we use PPO, which is just one of the many. PPO is not really memory efficient as well, so we can probably try GRPO. There's a lot we can do. But our primary end goal is to create a model that's both reliable and secure and generates good code in the end. So the key takeaway of this presentation is that sparsity is the failure mode in terms of binary credit in both security and functionality frameworks. And to fix this in small language models, we have to utilize some sort of curriculum or scheduling to get around the failure mode. Thank you. I'll take in any questions now.
Thanks. That was very timely. And okay, any questions? Great.
Hi, thanks for the talk. Sorry if I missed it at the beginning, but what language are you asking these LLMs to generate?
So for this, we focus on Python, and we have extended this to 3 languages, C++ and C as well.
And do the results vary by language in terms of syntax validity %?
So syntax validity does not really matter as much in terms of how or what language you're using. But for security, it's mostly that Python is very highly compile, and security is like, if we take both of them into account, Python is the most reliable, and C and C++, the LLM really, or the SLM really struggles with it for some reason. So yeah.
By reliability, you mean, or as in you mean the C and C++ programs are less secure than the Python ones?
Right, yeah.
Probably just because C and C++ are not memory safe?
I believe so, yes. So we tried 19 CWEs when we were testing for the security relevant prompts, and 8 of them were memory focused, and those were the most erroneous ones too. So yes.
Makes sense.
Yeah.
I guess that makes sense then. Thanks.
So do we have any other questions?
Yeah, just a short question. Thank you for the talk. So, because in the first slide you show the small model is DeepSeek, right? So, I'm just curious about what's the reason to choose this model. Is there what's the problem for the other small models? Yeah.
The DeepSeek 1.3 billion.
Oh yes.
Is it this one?
Yeah. So yeah, this one you said you are using DeepSeek model, and I'm just curious why you choose DeepSeek at this point. Is there any problem with the other small models? Yeah.
All right. So 1.3 billion parameters is like one of the lowest ones we can have that is fine-tuned for coding. That's one of the reasons. It's open source. That's another reason. So we started off with 7 billion parameter models, but this actually beats them with the whole pipeline. So it's sort of like setting up the lowest point we can train the model from and get our results high. Yeah.
I see. Sounds good. Thank you.
Yeah.
Any other questions? If not, let's give Suryansh a big hand. And I'd like to thank all of you for participating in this session. I want to thank the speakers. Let's give them all another round of applause. I think we had a great thing. And remember, the first talk was a candidate for Best Paper in the Conference Award. And there were 2 candidates, and this was one of them. And as organizer, do you want to say anything? So then we meet after lunch, so enjoy yourselves. Thank you again.